All right, let's jump right into it. In this explainer, we're diving deep into the actual, rigorous engineering behind sizing battery energy systems. We are stripping away all that marketing fluff to look strictly at the math, the logic that ensures your system is actually going to perform over its entire lifespan without any costly or, frankly, dangerous design errors. Because it really is the million-dollar question in solar design, right? Why do so many seemingly perfect off-grid systems just completely fail when you need them the most? You buy top-tier panels, you wire up a massive battery bank, everything looks absolutely flawless on paper. But the second you get a few cloudy days in a row or a really heavy load kicks on, boom, the whole house goes dark.
And when we get this sizing wrong, the consequences aren't just annoying, they can be catastrophic. We're talking inverters totally shutting down or overloaded cables that create a very, very real risk of an electrical fire. We aren't just looking at a frustrating power cut here. We're looking at what happens when you try to pull massive peak currents through a system that just wasn't built for it, causing severe voltage drops that will literally wreck sensitive electronics.
So to prevent those dangerous failures, here's our roadmap for today. We'll start by clearing up the classic power versus energy trap. Then we'll walk step by step through the engineer's blueprint for capacity sizing. And finally, we'll wrap up with the absolutely critical C-rate factor. Part 1, Power versus Energy, the root of system failures. Let's dive straight into this first massive trap, because confusing these two is honestly the secret culprit behind almost every major residential and commercial storage failure out there.
Look, 5 kilowatt label slapped on a box doesn't tell you the whole story. We have to separate peak load, which is that instantaneous demand, the power you need right this second, from the average load, which is the total energy consumed over time. Just think about walking into your kitchen. You turn on the microwave, a water pump, and click on an electric kettle all at the exact same moment. That massive instant pull, that's your peak load in kilowatts. But your average load in kilowatt hours, that's just the slow, steady burn of all your devices running over a full 24-hour period.
It really boils down to the sprint versus marathon analogy. Your peak load sizes your inverter to handle the sprint, those massive short bursts of demand. But your average load, that sizes your battery bank for the marathon. They are two completely different metrics, doing two totally separate jobs.
So now that we know we're sizing our batteries for that marathon, let's look at the actual 3 steps: basic capacity, actual capacity, and final capacity. This is the definitive calculation process the pros use.
Step 1, basic capacity. Building our foundation. This is where we get our raw, completely unadjusted starting number.
To find it, we take the total daily load in kilowatt hours and multiply it by our desired backup days, also known as your autonomy. If you're designing for a grid-tied home that just sees occasional outages, 1 day of backup might be perfectly fine. But if you're outfitting a true off-grid agricultural site, you might need 3 to 5 days of autonomy just to survive an extended cloudy spell. After that, we apply peak correction factors based on the specific user's load profile.
But here is the catch. You can't just guess with flat wattages. You have to accurately define that daily load by using a 30-minute interval profiling technique. By mapping out exactly when appliances are running in 30-minute chunks, you get a clear picture of the day-to-night split. The energy used during the day? Well, your solar panels can usually handle that directly. But everything running at night requires very precise battery sizing.
Step 2, actual capacity, the reality check. This is where we have to adjust for the actual real-world physics of batteries. Because let's be honest, a battery's nameplate capacity is basically a lie. You absolutely have to adjust for depth of discharge limits and state of charge reserves, and those vary wildly depending on the chemistry. If you're using a lead-acid battery, you are hard capped at a 50% depth of discharge. If you push past that, you're going to completely ruin its cycle life. Lithium iron phosphate, or LFP on the other hand, is the gold standard for stationary storage precisely because it lets you safely use 90 to 95% of the battery's true stored energy. And we aren't done cutting yet. You also have to slice out another 10 to 15% of that energy right off the top. Why? Well, you lose it to inverter conversions, line losses, and battery management system overhead. Your BMS needs to use some power just to monitor and balance the cells, and your inverter loses a few percentage points simply converting DC to AC power. All of these hidden taxes on your system have to be mathematically accounted for to find your true, actual capacity.
The takeaway here is absolutely crucial. Your system has to be mathematically designed to perform on its last day of life, not just commissioning day. Imagine a commercial frequency regulation system that perfectly hits its targets on day 1, but then falls short and breaches its contract in year 5 just because of standard expected degradation. That is an engineered failure.
Step 3, final capacity, future-proofing the asset. This is where we finally lock in the numbers.
To protect this asset for the long haul, you've got to bake in safety margins. You need buffers for inevitable battery degradation down to an 80% state of health, and you have to include temperature derating for hot climates. If you are installing a system in an incredibly hot location, say 45 degrees Celsius ambient temperature, the internal resistance increases. The battery physically cannot hold or deliver what it does in a perfectly climate-controlled 25-degree lab setting. Adding a 10 to 20% safety margin is what ensures true long-term reliability.
The C-rate factor, the power constraint. Finally, we have to bring this entire calculation back to our primary power bottleneck.
So, C-rate measures how fast a battery discharges relative to its total capacity. This means a battery might actually have all the required energy in kilowatt hours, but completely lack the discharge speed to start a heavy load. It's like plumbing. It doesn't just matter how much water is in the tank, it matters how wide the hose is to let that water out. Let's put this into perspective. A 10 kilowatt hour battery rated at 0.5 C, that's only going to deliver 5 kilowatts of peak power. But at 1 C, that exact same battery delivers 10 kilowatts. We are talking about the exact same physical footprint, the exact same amount of stored energy, but literally double the instantaneous output capabilities.
This proves once and for all that identical energy does not mean identical power. A 0.5 C setup, fine for basic backup like lights and refrigeration, but you need 1 C to handle those heavy surges, your AC units, your EV chargers, without the system totally faulting out. Imagine your client wants to charge their EV with a level 2 charger that pulls a continuous 7 kilowatts. If you've spec'd a 0.5 C battery that only outputs 5, well, that system is going to trip immediately. If you ignore the C rate and your inverter requests more current than the battery's limit, the battery management system steps in. It will immediately throttle the output, or worse, shut the whole system down completely. Cue those dreaded customer callbacks. The inverter and the battery have to constantly communicate. If the inverter demands more than the BMS decides is safe, the BMS just opens the contactors to protect the cells, and the lights go out.
So, as we wrap up this explainer, I'll leave you with a question to ask yourself on all your future projects. Is your system designed for the rigorous, unpredictable reality of real-world electrical loads, or is it just sized based on a misleading number printed on a cardboard box? Real engineering accounts for depth of discharge. It accounts for state of charge reserves, temperature derating, end-of-life degradation, and perfectly matched C rates. Master these elements, and you won't just build systems that work today, you'll build systems that last.